Good evening, everyone, and welcome to Hazards Ahead. I'm Michelle Stirling, your host for this evening's live stream, and this is it's part two of Robert Lyman's work on speed bumps on the road to decarbonization, or the world of net zero. So Robert Lyman wrote the report, and I will be providing commentary and walking you through a short PowerPoint, giving you some of the key highlights of the report. The report is on our blog and you can read it, or you can refer to this, and the live stream will be posted later so that people can watch it if they haven't been able to tune in right now. So please feel free to share it with your friends. And I want to thank everyone for joining in tonight. It's a beautifully hot evening here in Alberta. I'm talking to you from the climate cabin where we don't have any air conditioning and not even a fan. So it might be a little hot later on. But we won't be generating any extra GHGs, will we? We'll just be doing it the old-fashioned way with a ice block wrapped up in a towel, keeping me cool while I talk you through this PowerPoint. First of all, I want to invite you to become a member of Friends of Science Society. We're a small group of dedicated people who believe that there should be open civil debate on climate and energy topics, especially now that some of these extreme decisions are being made to move to full electrification. And we'll be talking about some of the implications of that tonight. So you can become a member on our main website, www.friendsofscience.org. There's a little donate membership button up in the corner, or you can just donate if you'd like, or you can just share our material with your friends and family and start a conversation and see if you can open up the debate a little bit. That's really, really important, especially now that people like Mark Carney are pushing for all kinds of extreme measures. The Deutsche Bank out of Germany has called for an eco-dictatorship. So, we're moving far beyond the realm of simple environmental protection or climate change. We're moving way off the rails, and we need everybody to be informed and be able to discuss the options. So I just want to also thank our board of directors and our team at Friends of Science. I'm the face of Friends of Science, but behind me there's a dedicated group of volunteers, and I also want to thank my technical producer Jay for helping me out tonight. And let's get on with the show. Enough blabbing from me. So, as we said, hazards ahead. This report was written by Robert Lyman. Robert Lyman was a federal public servant for 27 years. He was a diplomat for 10 years. He's got a very good geopolitical view and many insights on how these policies will affect all of Canada and many other countries in the world. So tonight's presentation draws on research from a few different places in the world. Let's go on with the show. The overview is that Robert Lyman examines the technological and cost barriers to the conversion of much of the world's economy to electricity as its primary energy source in place of fossil fuels. And we'll look at electricity storage, like that would be pumped hydro and battery storage, the electrification of the light-duty vehicle fleet, the electrification of railways, the electrification of residential heating and cooling, and the feasibility of meeting the mineral supply requirements. And also, there are some serious geopolitical risks in decarbonization that we'll discuss. Things that I haven't heard anything about in the media. And there's a helpful reference here for understanding power generation from the US EIA. So we will progress to electricity storage. So wind and solar are intermittent forms of energy capture and conversion, but they often produce energy when it's not needed. Wind in particular will generally produce a lot of power in the evening and at night, but that's not the peak demand time. Solar, of course, produces most during the day and at high noon, but then rapidly drops off in the evening. And the peak power demand usually is very early in the morning and early afternoon, early evening, from about 4 until 8 or so. So people say, oh, well, we'll just go to using storage because that would solve all of our problems. You can see these batteries here. These are grid scale batteries. But grid scale storage is the holy grail of wind and solar, meaning it's not something that's been discovered yet. Pumped hydro is another means of storage. So let's look at pumped storage first. Pumped storage provides about 97% of the grid power storage in Canada and the United States. Expansion of pumped storage reservoirs and facilities is possible, but there are relatively few sites available that would be suitable for it. Canada's only pumped storage hydro facility is the Ontario Power Generation's Sir Adam Beck Pump Generation Station. This is a 174 megawatt facility. It pumps water from the Niagara River into a 300 hectare reservoir for energy storage. And this storage capacity is greater than what currently exists in all of Canada's newer emerging storage technologies such as batteries. A third channel feeding the 174 megawatt pump generation station, this gives you the coordinates, which pumps water up into the man-made reservoir at night and generates electricity during the day, feeding the water back to the Sir Adam Beck generating complex. So you can see this is a massive facility here, and of course quite a bit of cement was used in building that, and cement is full of CO2. So anytime you're planning to, or the making of cement requires the emissions of a lot of CO2. So anytime you're planning to do this type of work, there will be a lot of embedded emissions. If we look at how pumped storage works, this is from the CER site of Canada. So in general, when there's a lot of energy consumption and when there's a lot of energy generated, the water is pumped into storage and then it can be released at a later date for consumption. But what's very important to note here is the United States has over 30 pumped storage hydro facilities with a combined capacity of 22 gigawatts. The US facilities generate around 23,000 gigawatt hours per year, but they consume 29,000 gigawatt hours to operate their pumps. So this is actually a net loss of energy. But the grid reliability provided by these facilities and the ability to generate when demand is strong is highly beneficial and will become increasingly important as Canada and the US integrate more renewable power into their grids. So let's just think about that for a moment. What that means is that, for instance, people are planning to pair wind and solar with pumped hydro facilities. And so when the wind is blowing strongly, let's say in the evening, then it could pump water up into some reservoir. And then later, when certain drop-offs might be experienced, say in wind power, or when the grid needs a little bit of transitional power, then that pumped hydro would be released and it drives a turbine to generate electricity. So that all sounds good in principle, but there's a limit to how much can be stored. Like, this is not long-term storage. This is for short transitional periods. And the cost of these facilities are fairly significant. Let's have a look and see. So pumped storage costs about $2,000 per kilowatt, US dollars. Grid scale battery storage costs about $2,500 per kilowatt for a discharge duration of about 2 hours or more. So that's not very much time. And the longer the storage is needed, the higher the cost. So Roger Andrews, a geophysicist with worldwide experience in the energy and mining industries, has estimated the combined wind and solar levelized cost of electricity without storage to be $50 per megawatt hour US and at least $700 US per megawatt hour with it. So that's a enormous par. And his estimates are in a range similar to that of the Clean Air Task Force, which is a Boston-based energy think tank, and as reported by the MIT Technological Review. So battery storage, in short, is not an option that will ensure an affordable energy future based on high levels of renewables generation. So storage is costly. And as we saw, it's limited, quite limited. Now, several countries, how about the electrification of the light-duty vehicle fleet? Several countries and subnational jurisdictions have publicly committed to eliminating sales of internal combustion light-duty vehicles as early as 2035. So internal combustion, that's like a gas engine, diesel engine, and they want to get rid of those, or certainly not sell them anymore. But by 2019, battery electric vehicle sales, BEVs, constituted 0.77% of the global light-duty vehicle fleet, and only about 1% of vehicle sales. So you can see that that's nothing compared to the millions of cars sold worldwide every year. And according to Statista, worldwide car sales are expected to grow just under 70 million automobiles in 2021, up from an estimated 63.8 million units in 2020. So it doesn't seem very realistic to set this kind of a goal when there's not that much demand for those kind of cars, and of course there are other challenges with them. Let's look at some of the problems of powering EVs. So recharging a battery electric vehicle with a 64 kilowatt battery at home with a level 2 240 watt charger requires up to 10 hours. So that can be done overnight, but of course only if you have a home that's wired for that, and probably with a garage, because you're not going to be running cables across the street. And so, you know, think of the number of cars in your city that park on the street. So not everyone will have access to a home charger. So electric vehicle owners living in a townhouse or a row house or an apartment without access to a level 2 charger would have to rely entirely on the public fast charging network. And a significant number of people who park their cars on the street would also be dependent on the public fast charging network, which in most countries is quite immature. And you can see here this shot of Merit, the supercharger, and the lineup of Teslas waiting to charge their cars in that 46.6 degrees Celsius heat. So that's not very promising, is it? Now, at the end of 2019, the UK had around 100,000 battery electric vehicles, which represented about 0.3% of the light-duty vehicle fleet. And that's the reference to an author on that topic. These numbers would have to increase by at least 300-fold if the UK government is to replace all light-duty vehicles. And further, if one were to assume a very unlikely 100-fold increase in battery electric vehicle numbers to 2030 to 10 million, this would represent only 27% of the light-duty vehicle fleet. So 85% of UK transport would still rely on internal combustion vehicles. In 2019, 37,800 battery electric vehicles were sold in the UK. At this rate, it would take 263 years to reach 10 million units. So I think you can see that we're dealing with a bit of fantasy land here. And sadly, it would seem that there's no actual cost-benefit analysis being done by governments to assess things in the manner that are being assessed by Robert Lyman and these other authors. And the public, therefore, are being misled. And they believe that just simply making a law, you know, say like the Climate Accountability Law, Bill C-12, well, we can just require governments to meet targets, and we can just require people to buy EVs. But if there are not enough EVs being produced, if there are not enough charging facilities for them, if there are not enough power generation plants to back up the additional demand for electricity, we're going to find ourselves in a pickle. How will people commute to work? How will people get deliveries to and from stores of goods that need to be sold? How will Amazon operate? So, these are issues that will affect daily life very soon, unless proper cost-benefit analysis is done and proper planning, because the goals that are being set are not realistic, as you can see. And here's another very unrealistic goal. This is the electrification of railways. So this has also been proposed, the electrification of freight railways in the United States and Canada. This would require the building and maintaining of a high voltage catenary system. So this is kind of like, with streetcars, where you see that there's a power system that comes from this network of lines. And this would, in the States, would span close to 140,000 miles in a wide variety of geographic locations. Like if you're going downtown with this kind of a system, or between two cities on a flat plain, it's not such a big problem. But if you're trying to run this through mountain pathways, over narrow bridges, through tunnels and such like, you may be required to rebuild much of the infrastructure at a cost of billions of dollars. So this would probably require delivering electricity through thousands of rail tunnels, rebuilding major bridges to provide clearance and support for the catenary wires. Because these kinds of systems also do go down from time to time. And there's a link in the PowerPoint for Amtrak here, and it tells you a bit more about it if you'd like to read that. And so what would the cost of that be? Well, the complete electrification would require conversion of 140,000 miles of rails. The minimum direct capital cost would be in the order of $280 billion, and a probable cost much higher. And to that should be added the cost of replacing the more than 24,000 Class 1 locomotives in the existing fleet, because they'd all have to be electrified instead of being diesel electrics, which according to the Association of American Railways would be close to $100 billion. And of course, these costs do not include the cost of adding the electrical generation capacity that would be needed, for which no current estimates are available. And if we just go back to, speaking of power generation, just thinking back to the issue of electrifying the light-duty vehicle fleet, Kent Zare, who's a professional engineer, did an assessment of the EV policy for Canada. And based on a conversion of the BTUs of gasoline use in Canada, we would have to build 10,000 megawatts more electrical generation, and that would just be for the light-duty vehicle fleet. So 10,000 megawatts more, that would be like building 8 additional Site C dams, or 8 additional Muskrat Falls, 8 or 10 of each of those. And each of these projects take about 20 to 30 years from start to operation. And there's not one new power plant on the table right now. And as you know, Site C Dam and Muskrat Falls, they're both way over budget, and they both have serious technical problems. So, we're basically implementing policies for which we don't have the power generation to support the policy. And that creates a very dangerous situation, because if we get partway in and spend billions of dollars building the part of these facilities, but then we don't have the power generation to back up, that might mean that certain industries would have to be curtailed, or that you, the consumer, would have your use of electricity curtailed. And that could be very devastating to our economy and to citizens. So let's continue here with the railways, going back to the railway. So I was just commenting now, it doesn't include the cost of adding additional electrical generation capacity. And if the cost of converting the present system of railways to an electrified one were placed on current industry, it would impose financial risks that many would be unwilling to accept. Again, many of these industries, they're planning decades in the future. And to impose this new change in operation through laws, legislation, regulation, they might just say, well, you know what, we're not going to run over railway anymore at all. So, so ultimately that means that the conversion would have to be funded in part or in whole by governments, meaning you, the taxpayer, with the costs and risks largely borne by taxpayers. So there's a link here to this interactive map, and it takes you to all of the railways in North America. So quite a network there. How about the electrification of residential heating and cooling? So there is a proposal to go completely off natural gas and instead replace natural gas heating in the home with electrification. Again, the problem arises, where will all the power come from? It won't come from renewables as we saw at the beginning. It won't come from storage. That would be far too expensive and unreliable. And how much would it cost? Sometimes people are saying, well, we could do geothermal heating, or we could use heat pumps, geothermal heat pumps. But the best studies of the probable costs of decarbonizing housing have been done in the UK. A major pilot project there concluded that emissions could be reduced by 60% for an average expenditure of £85,000, which is 146,000 Canadian dollars, and by 80% for an average expenditure of 135,000 pounds, or Canadian $231,000. So assuming that these costs could be significantly reduced through some kind of national effort, Professor Michael Kelly concluded that most existing UK residential housing stock could be retrofitted for a cost of about, just £70,000 each, or £2 trillion, or Canadian $3.43 trillion. So you can see that these are astronomical costs, and ordinary people could not put up this kind of money. In 2016, the Energy Technologies Institute estimated that the cost of deep retrofits in the UK housing stock was more than £2 trillion. And in 2018, the Institute of Engineering and Technology published figures of £80,000 to £90,000 per home. So I would say that most ordinary people would question the wisdom of their governments asking them to switch out natural gas in their home for this very expensive alternative, especially when you look at the climate change science. If you look at Bjorn Lomborg's book, False Alarm, you'll find that he did an experiment. He used the computer model, the computer simulation that the Intergovernmental Panel on Climate Change uses for its estimates, the MAGIC computer system, and he found that even if all the countries met their Paris targets, the reduction in warming by 2100 would be 17/100ths of a degree Celsius. So that's not necessarily going to keep the world under 1.5 degrees Celsius. So on the one hand, you're being told that if we do this, we'll achieve the targets, we'll achieve the Paris Agreement goals. On the other hand, reality, math, and this simulation that the IPCC itself uses shows that that's not the case. So in fact, you're being snowed. So keep that in mind. And snowed for a lot of money. So let's have a look at what trillions of dollars actually are. So taking into account the cost of adding electricity generation based on wind and including heat pumps, the cost per house could rise to £150,000 Canadian, $257,000, a $250,000, or a national total approaching £4 trillion Canadian dollars. That would be $6.85 trillion. So here you can see that $1 million is this much if these are packs of $10,000. And if you use the same package of 1 million, here's 100 million. Here's how much that is. And if you want to show a billion, there's $1 billion. Here's what $1 trillion looks like. These are double stacked pallets using this as the unit. So when we're talking 4 trillion, 6.8 trillion, this is a lot of money. This is money that your children, your grandchildren, your great-grandchildren, God knows how many generations will be staggering under the burden of this money. And for no benefit. We don't see that there will be a reduction in warming. It will not stop extreme weather events. So here's another problem, and that is all of these new things require additional minerals, and many of them are unique minerals. The system that we have now uses common minerals that are found in almost every country of the world. But if we're building EVs and if we're building wind and solar devices, these require special rare minerals that are only found in a few places of the world in quantity. And that creates some problem. First of all, we'd have to open many more mines, and it takes a long time for a mine to become operational. Like first you have to stake out where the particular mineral is found, you have to get the permits, you have to do all of the assessment process, you have to get the financing together. Then you begin the groundwork, but it takes a long time before that mine is actually operational and delivering materials for production. And so let's have a look at some of these numbers, see what that's all about. So the Manhattan Institute, Mark Mills, has examined the physics of fueling society, including the potential for wind, solar, and biomass energy sources to meet the energy requirements which are now met by conventional energy sources. One of his key findings was that the building of wind turbines and solar panels to generate electricity, as well as batteries to fuel electric vehicles, requires on average more than 10 times the quantity of materials compared to building machines using hydrocarbons to deliver the same amount of energy to society. 10 times. That's ridiculous. In May, and the IEA even, the International Energy Agency, in May 2021, they issued a report called The Role of Critical Minerals in Clean Energy Transitions. And the report projected that the demand for key minerals like lithium, graphite, nickel, and rare earth minerals would explode, rising by 4,200%, 2,500%, 1,900% and 700% respectively by 2040. So of course in the investment community, people are rubbing their hands with glee thinking, oh fantastic, my copper mine will take off, my lithium mine, my nickel, and they probably will take off. But as the IEA points out, the world does not have the capacity to meet such demand, and there are no plans to fund and build the necessary mines and refineries. And furthermore, demand will drive up costs dramatically, and there's an unrealistic timeline. So, in addition, sharp increases in demand for these metals will raise commodity prices, which in turn will raise the prices of many other goods. Like once you affect any part of the critical supply chain of energy or materials, then everything else starts to rise with it. And as I mentioned before, for mining, it takes over 16 years for mining projects to go from discovery to the first production. And yet, if countries started tomorrow, new production for these materials might begin after 2035. So just this information alone places into context the claims by governments of the US, the UK, and Germany, and even Canada, that they will have carbon dioxide-free electricity by 2035. It's just not going to happen. And this article is quite interesting about these different mines. Now, there's another problem that's not being addressed at all. The world's superpowers are superpowers because they have abundant supplies of energy. Energy security is one of the most important things that a country can have. And these plans are putting the security, the national security of many countries completely at risk. Canada has an abundance of all the resources mentioned, all the energy, all the hydrocarbons, coal, natural gas, and oil. We have the third largest reserves of oil in the oil sands. And our competitor nations are not going to stand by and go, yeah, let's go to wind and solar. No, they're plowing ahead with the energy-dense opportunities that they have, and they'll be laughing at us as we put ourselves at risk. And especially electrification severely puts the country at risk, and I'll explain why. So there are significant but often ignored security risks. The top 3 producers of 3 key green energy materials control more than 80% of global supply. So China's share of refining is about 35% for nickel, 50 to 70% for lithium and cobalt, and almost 90% for rare earth elements. Russia is in a dominant position in the supply of natural gas to Western Europe, as you can see here. And by comparison, the top 3 oil producers, including the United States, account for less than half of the world's supply. So, North America and Europe are largely trying to decarbonize and not use fossil fuels anymore. But China, India, Brazil, Turkey, all these countries are booming, and they're going to progress and continue to use high-density fuels like coal, natural gas, and oil. And this little map here comes from the United States Geological Survey. So if you want to have a look at the link here, that will show you where the distribution of critical minerals are in the world. But there's an even greater security risk. So what alternative if sabotage, a CME, coronal mass ejection, or an EMP, an electromagnetic pulse, interrupts power supply? So this is a picture of a coronal mass ejection. It's a big solar flare coming off the sun. And in fact, right now, I think if you go to the Solar Dynamics Observatory of NASA, there is a solar flare that is hitting Earth at this moment. There should be an aurora tonight in many parts of the northern hemisphere. But the most important security risk of all resides in the possibility that having completely electrified Western economies and then achieved high levels of reliance on wind and solar energy for needed generation, there might be major interruptions in power supply because of weather, the failure of transmission systems, cyber attacks, or sabotage. And this would be like space weather. There's an event called the Carrington event that happened in the late 1800s, and it was a huge solar flare. It actually lit telegraph lines on fire. And in the late 1980s in Quebec, there was also a big solar flare that hit Quebec. And of course, Quebec Hydro is an amazing power producer, and they have a lot of those very big pylons, high voltage lines, transmission lines all over the place. But it's on the Canadian Shield, which is very conductive form of geology. So the blackout hit, I think, about a quarter of North America. That whole eastern seaboard went to blackout because of the CME that hit and fried a number of transformers. And I'm talking about these really big transformers. It fried it in seconds, and it just looks like tinfoil after you throw it into a campfire. Those transformers take months and years to replace. They're not an off-the-shelf product. So, we could be facing like national blackouts with this kind of space weather event. We could also have just a regular weather event, a very severe winter storm, again in Quebec, and oftentimes in Ontario. There are these big ice storms that take down those pylons, take down power lines. Then what would the alternative be? It would be kind of like in Texas, where people ended up sleeping in their car because they could actually, or their truck, because they could power up their diesel truck, turn on the heat in the truck, and stay warmer than in their house. And some of these trucks even have a little generator on board, and so they could, cook food and boil water, and everything that they needed was actually in their internal combustion vehicle. But if you had an EV at that time, you were out of luck. So the economies of Western countries would be at risk of severe and prolonged blackouts, and we wouldn't have an alternative capacity available, which we have now. So right now, if you choose to drive an EV, great, fine. You're in the minority, but that's fine, and you can probably get service in most places. But if everyone was driving an EV, imagine that in winter on, say, the 401, a big traffic accident, everyone's stuck on the highway there. How would you power up all those vehicles? How would you deal with the human tragedy? People would be freezing in their cars. So the contemplation of this possibility of a national risk flies in the face of all the lessons about energy security that Western countries should have learned since 1973. And that was the oil shock of 73, 74. And that's actually where a lot of the renewable energy plans came from, because people wanted an alternative to relying on OPEC nations. But in the interim, there's been a lot of oil and gas discovery all over the western part of the world. And in fact, until the Biden administration, the US had become a net exporter of oil rather than an importer. And it is kind of ironic, Robert Lyman notes, that the IEA, whose establishment was initially inspired by the need for increased energy security, should now largely ignore this consideration. So this is a failure to learn from history. And I just want to mention another thing here. I had noted in the previous slide that there might be something called an EMP. This is an electromagnetic pulse. This is a weapon of war where a bomb could be set off at a certain height over a centralized area that would set off an EMP pulse that would black out all of the electricity in the region below. So these things exist, this can happen, and if you don't have an alternative to an electrified society, then you will certainly not be able to fight back in any way, or perhaps even survive. So it's a very serious risk, and we should be considering it. So So we have these two reports. The one that we just discussed today, Hazards Ahead, is posted on our blog. And we have the previous one where we have a live stream already posted, and we have the report. We also have the PowerPoint and additional links that I had mentioned in that live stream. So have a look at our reports, share them with family and friends or influential people. And if you like the work we do, please donate or join us. There's a little button here. It's the same button that's on our website. We'd love to have you as a member. And just so that you know a bit more about us, Friends of Science Society is an independent group of Earth, atmospheric, and solar scientists, engineers, and citizens that is celebrating its 19th year of offering climate science insights. After a thorough review of a broad spectrum of literature on climate change, Friends of Science Society has concluded that the sun is the main driver of climate change and not carbon dioxide. And we're not the only people who think that. There are quite a few scientists who agree with our perspective. And you may wonder why this doesn't appear in IPCC reports. Well, the Intergovernmental Panel on Climate Change has a mandate to examine the human causation of climate change, not all causes of climate change. And that's what their focus is. So that's why they generally don't report in any depth on the natural causes of climate change. So there are two other groups out there. One is called the Non-Governmental International Panel on Climate Change, which has issued a couple of reports. One of them is called Climate Change Reconsidered, and that will give you more perspective on the natural causes. And if you want a slightly simplified version, you could go to clintel.org. Clintel is a group of about 900 scientists and scholars from around the world, and their view is that natural factors are more influential than human causation on climate. They also do not agree that there's any kind of climate emergency. And they have some more plain language essays. They have the World Climate Declaration and a climate essay that's quite straightforward. And also on our website, on our main page, we also have a climate science essay that's quite thorough and in-depth, put together, compiled by Ken Gregory, professional engineer and our research director, and he's got a lot of updated graphs there. It contains many different graphs showing climate science evidence. And what people need to realize is that many of the catastrophic claims that are made in the media and by various activists out there like Zipporah Berman or David Wallace Wells, Al Gore, Greta Thunberg, these are based on climate models. They're based on simulations, and none of the simulations are actually matching the present observed data. They're way above the present observed data. That's where the catastrophic thinking comes from. And they also can't replicate what's called hindcasting. They can't replicate the medieval warm period. So if you look back in history, we're at a warm period now, but before this we were in the Little Ice Age, which was quite a bit cooler, very cold, so cold that birds froze, they dropped from the sky. And before that was the medieval warm period. That's when cathedrals and castles were built, food was abundant, and people were having a very good life. So when they put all the information into these climate models, they predict too hot for the present, and they cannot replicate the past. So if the computer simulation was accurate, it should be able to replicate the past, and it should be much closer in the present. So those are some things to think about. You can go through our climate science essay and see some of the graphs. And of course, feel free to send us some questions. And I'm just going to check now and see if there are any questions from the chat. So pardon me for a moment while I look and see. I did want to mention, I don't know if you've seen our video, but recently the upcoming IPCC report was leaked to the press in France. The IPCC report, the new one, is not supposed to be out until 2022, and no one should be leaking a draft at this point to the press. And of course the press went crazy, picked out all kinds of scary headlines. Tipping points are going to be reached and everything will be awful. Okay, I don't see any questions here. But that's not the case. Tipping points are things that are very popular with the Potsdam Institute out of Germany. And I guess if you look in geopolitical terms, if you look at Germany and Switzerland and Sweden, where a lot of this climate catastrophe thinking comes from, these are all very small countries compared to Canada. So, of course, they see that the end is nigh because they have to import a lot of fossil fuels, especially Germany. Germany imports something like $600 billion worth of coal, natural gas, and oil every year. And they're not importing it from us. They're importing it from despot nations. So, it is rather hypocritical of these people to go on and on about whether or not Canada has high human rights standards here when they're importing from some of the worst places on earth. And certainly with respect to Greta Thunberg and her Swedish virtue signaling, the largest oil play offshore of Norway is called the Johan Sverdrup, and that was discovered by London Energy of Sweden. So they're busy drilling there as much as they can. So it's pretty hypocritical of her to come here and criticize Alberta. Just gonna have, oh, here we have some questions coming up. Okay. One person would like to know more about ammonia-driven energy batteries and what we really need to be doing. I don't have any information on that right now, but we can look that up if you want to post an email or send us a note to media@friendsofscience.org. We'll find some information for you. Another person says that I remember the 1998 ice storm here in Ottawa. I was able to look out my apartment window and watched transformer after transformer explode and catch on fire across the river in Gatineau. Yeah, so those would be like the street transformers, the little round ones, I'm assuming. And yes, they will also blow up. I understand that in California, that's part of the challenge with the growing number of EVs there, that these transformers and the regional distribution lines were not actually designed to carry that load of these additional cars. Thank you for that insight on that Ottawa storm. And we have another one. Has anyone looked into pole shifts? So this is, I presume, regarding the magnetic poles of the Earth shifting. I won't talk in detail about it because I don't have the information at my fingertips, but I do know that the North Magnetic Pole has been moving quite rapidly. It used to be in Canada, and now it's somewhere in Siberia. And I understand that some airports around the world have had to change the markings on their runways to accommodate the changing magnetic fields. So you can look it up on the internet. There's quite a bit on the fact that the poles of Earth have shifted in the past. And I'm not going to say much more because I'll get myself into trouble talking about something where I don't have the material at hand. But it is a natural phenomenon, and it's something that I believe the Inuit have noticed, because they have noticed changes up north that are not necessarily climate change per se, but would be related to this kind of change in the poles. So that's also a factor in climate change. There are many factors related to the geomagnetic activity on Earth, the interrelation between us and the sun and other major planets like Jupiter and Saturn and Venus, the conjunction of the planets and the orbital patterns and changes and stresses. The climate system is extremely complex, and it's affected by more than just the things on Earth or just the things that humans do. We do have an impact. I think Roger Pielke Sr. has written a number of very good papers, he and his colleagues, on how land use and water diversion and deforestation and agriculture affect regional climates. Quite interesting work, but of course it's something that's hardly ever considered as part of the IPCC's review. And it's not something that we can necessarily do a lot about in many cases. Of course, we need agriculture because we'd like to eat. But if we better understood those impacts, then we could also better manage our regional climates, perhaps. But I hope that you'll have a look at our website, because we've got lots of material on there. We've also got it marked as to whether the technical difficulty is high or low. So for those of you who are not really into the detail of the science, you can just look at the articles with the 1 star. For those of you who prefer the in-depth scientific review, there's lots of them with many more stars than that, indicating a higher technical difficulty. So let me see if we have any more questions here. Okay, we have a comment. The Neglected Sun by Fritz Varenholt. Yes. And this individual is saying, yes, climate models are not science. Yes, The Neglected Sun is by Fritz Varenholt. Varenholt is a very interesting person. Dr. Varenholt is a chemist. He's one of the early environmentalists. He wrote a book called Sevastopol, Could Be Everywhere. I think that's the title of it. And this was back in the 70s. So he was looking at chemical factories and the risk of a catastrophic event at a chemical factory and how that could really harm large groups of citizens or nature and rivers and such like. And he went on to become an executive with one of the renewable energy companies in Germany. And they put up a wind farm and it wasn't performing that well. And he was trying to figure out why, and he realized in discussion with some other scientists that there had been a change in some of the solar dynamics that were affecting the wind patterns. And the more that he looked into this, the more he realized that the sun is actually driving climate change, and the whole CO2 theory is, a bit exaggerated. In his view, he still believes that our CO2 emissions should come down. But he also says that we do have time, there's no rush, and we don't have the proper technology yet. And most important, we should be looking at how the sun affects climate. So he wrote The Neglected Sun with Sebastian Lunning, and they've done a number of peer-reviewed papers as well on the same topic. And also, if you've ever seen the movie called Global Warning, which is by, I was just pronouncing the N there, Global Warning, by Matthew Embry. He does quite a nice interview with Dr. Varenholt. It's very informative. So you can see the link to that movie on our YouTube channel under the interviews with director Matthew Embry. You can read The Neglected Sun by Dr. Varenholt and Sebastian Lunning, and he's also got another book out, but I think it's only in German right now. And we did have a little blog post on it on our website. I don't quite remember the name of the book. So anyway, let me just look and see if we have any more comments. Oh, another comment and another question. Okay, this is a very good point that I didn't make in the presentation, that electricity is not primary energy. So we produce electricity by consuming fossil fuels, nuclear, and unreliables, as this commentator calls them. But that's true. Like, electricity has to be made. So it's, many people think you just plug into the wall and there it is, but in fact it's coming from a power plant that's burning something or using nuclear power. And we have another one. We have a question here, what is primary energy? So primary energy is the use of fossil fuels to create energy. So I don't see any other comments there. So I think we're going to wrap up for the evening. I want to thank everyone for joining us tonight. I want to thank my technical producer, Jay. I want to thank our board for their support of this kind of work that we do. And I hope you'll have a look at Robert Lyman's reports. We've got several of his reports online. He's got so many insights, and unfortunately, of course, the press doesn't pick up our reports because we're locked out as quote-unquote deniers, when we're actually just trying to explain some of the nuances that people need to understand in order to make good judgments. So again, I'd like to thank you all, and I hope you'll join us again for another live stream. We'll be doing more of these. And come back and join me here at the Climate Cabin somewhere in Alberta. Thanks very much for joining us tonight. For Friends of Science Society, I'm Michelle Stirling. Good night.